A star is one of the simplest objects in the universe to describe, and one of the most consequential. It is a self-gravitating sphere of plasma, held up against its own crushing weight by the outward push of pressure, and for most of its life it shines by fusing hydrogen into helium deep in its core. We can never bring one into a laboratory, so almost everything we know about stars we have wrung from their light alone. And yet that turns out to be enough because, remarkably, a star's entire observable character is set by just a handful of fundamental numbers: its mass, its chemical composition, its age, and to a lesser degree its rotation and magnetism. From these few inputs, everything else about the star follows. The quantities we actually measure or derive are a small, tightly linked set. There is the effective temperature, a single number standing in for the temperature of the star's visible surface, defined as the temperature of an ideal blackbody that would radiate the same power from each patch of area. There is the luminosity, the star's total radiant power, the energy it pours out every second in every direction and at every wavelength. There is the radius, the surface gravity that follows from mass and radius together, and the chemical abundances written into the light. The luminosity is intrinsic to the star, and it must be kept carefully separate from the apparent brightness we see in our sky, which is diluted by distance, and tells us as much about how far away a star lies as about how fiercely it truly burns. Every one of these properties is measured against a single yardstick: the sun. In 2015, the International Astronomical Union fixed a set of official nominal solar values so that astronomers everywhere would speak the same language: a nominal solar luminosity of about 3.8 times 10 to the 26th watts, a nominal surface temperature of 5,772 Kelvin, and a nominal radius just under 700,000 kilometers. The sun's mass, about 2 times 10 to the 30th kilograms, is quoted indirectly through the very precisely measured product of gravity and mass, because the gravitational constant itself is the least well-known number in physics. From here on, stellar masses, luminosities, and radii are all expressed in solar units, the natural currency of the entire field. When you pass starlight through a prism or a grating, the smooth rainbow is interrupted by a picket fence of dark lines, wavelengths at which atoms in the star's cooler outer atmosphere have absorbed the light rising from below. That pattern of lines is a fingerprint, unique to the star's temperature and composition, and learning to read it is the foundation of all stellar classification. The system we still use was born at the Harvard College Observatory around the turn of the 20th century, funded by the estate of Henry Draper, the first person ever to photograph a stellar spectrum. The monumental labor of classifying hundreds of thousands of spectra fell largely to a team of women, the so-called Harvard computers. One of them, Williamina Fleming, first lettered the spectra A, B, C, and onward, in order of the strength of their hydrogen lines. It was Annie Jump Cannon who turned that clumsy alphabet into something profound. She dropped the redundant classes, merged others, and reordered what survived so that the spectra formed one smooth, continuous progression, and the result is the famous deliberately scrambled sequence OB-AFGKM. It runs from the hottest, bluest stars at the O end to the coolest, reddest at the M end. Each letter is split further by a digit from 0 to 9, so that our own sun is precisely a G2. Cannon personally classified something like 250,000 stars, at a pace no one has ever matched, and the great catalogue she built is still consulted today. Generations of students have memorized her sequence with the mnemonic O, be a fine guy, kiss me. Each class has its own signature. The blazing blue O stars at 30 to 50,000 degrees show the lines of ionized helium. The B stars show neutral helium. The A stars around 10,000 degrees show hydrogen at its most dramatic. F and G stars like the sun show a whole thicket of ionized and neutral metals. The cooler orange K stars are dominated by neutral metals, and the coolest red M stars below about 4,000 degrees are cold enough that whole molecules like titanium oxide survive to stamp broad dark bands across the spectrum. Later astronomers extended the sequence downward with the classes L, T, and Y, into the twilight realm of dwarfs, failed stars too light ever to sustain hydrogen fusion. But the Harvard workers built all of this purely by eye, by matching line strengths. They did not yet know what physical thing the sequence was actually measuring. The answer was hiding in plain sight, in the overall color of the light. To a good first approximation, a star glows like a blackbody, an idealized radiator whose spectrum depends on temperature and nothing else, and a blackbody obeys a beautifully simple rule, Wien's law, The wavelength at which it shines most brightly is inversely proportional to its temperature. A scorching O star peaks far out, in the ultraviolet, and looks blue-white. The sun peaks in the green-yellow. A cool red dwarf peaks down in the near-infrared and glows a dull red. This is why color is a direct, if rough, thermometer for the heavens. Bluer means hotter, redder means cooler, and it is the single most immediate fact you can read from a star with nothing but your own eyes. Astronomers make this precise by measuring a star's brightness through two different colored filters, classically a blue one and a visual one, and taking the difference, a quantity simply called the color index. A red, cool star has a large color index, a blue, hot star a negative one. The great practical virtue is speed. You can measure a color for a faint star far faster than you can spread its light into a full spectrum, and so color lets us survey not thousands but billions of stars. The enormous color magnitude diagrams that modern surveys produce are the direct descendants of this simple two-filter trick. Real stars are never perfect blackbodies. The absorption lines and the wavelength dependence of their opacity see to that. But the blackbody picture is the indispensable first approximation linking what we can see, color, to what we truly want, temperature. But there was one genuine puzzle the Harvard classifiers could not solve, and it concerned hydrogen. Hydrogen is by far the most abundant element in every star, so you might expect its visible absorption lines to be strongest in the hottest stars, where there is the most energy to go around. Instead, those lines peak in the middle hotter stars, around 9 or 10,000 degrees, and fade away toward both hotter and cooler stars. Explaining this took two pieces of new physics and one extraordinary insight, from Meghnad Saha, and then from Cecilia Payne-Gaposchkin, whose 1925 doctoral thesis proved both that the spectral sequence is fundamentally a ladder of temperature, and that stars are made overwhelmingly of hydrogen and helium, a conclusion so radical at the time that she was pressured to soften it. The resolution is a tug-of-war between two competing effects. The visible hydrogen lines are produced only by atoms whose electron sits in the second energy level, poised to absorb. The first effect, described by the Boltzmann equation, says that as a star grows hotter, more of its atoms are kicked up into that second level, so the lines ought to strengthen with temperature. But the second effect, described by the Saha equation, says that as it grows hotter still, the atoms begin to lose their electrons entirely. They ionize, and an atom stripped of its electron has no lines left to give at all. The strength we observe is the product of the two. Below about 10,000 degrees the first effect wins and the lines grow. Above it ionization wins and they collapse. The crossover, the peak, lands squarely in Class A. That very same competition, played out element by element, explains the entire sequence at a single stroke. The lines of ionized helium demand the ferocious heat of the O stars. Neutral helium peaks, a little cooler in the B stars. The ionized calcium that dominates the sun's spectrum is there precisely because at around 6,000 degrees calcium is mostly singly ionized, and in the coolest stars the temperature finally drops low enough for fragile molecules to form and endure. So the Harvard sequence, assembled by hand and eye with no theory behind it at all, turned out to be almost a pure ranking of stars by the temperature of their surfaces, one of the loveliest cases in all of science of an empirical pattern, later revealed to rest on a deep physical cause. Temperature, though, is only half the story, because two stars at exactly the same temperature can be wildly different objects. A cool red supergiant and a cool red dwarf share a surface temperature, but differ by factors of thousands in size and in brightness. To capture that second dimension, 3 astronomers at Yerkes Observatory, Morgan, Keenan and Kellman, published in 1943 a two-parameter scheme that adds to the temperature letter a luminosity class written as a Roman numeral. It is still the standard today, and it lets a single spectrum reveal not just how hot a star is but how large. The luminosity classes run from the most to the least luminous at a given temperature. Class 1, the supergiants, the brightest of all, Class 3, the ordinary giants, Class 4, the subgiants, and Class 5, the main sequence stars that astronomers, a little confusingly, call dwarfs. The white dwarfs sit outside this scheme entirely in a category of their own. Under this system our Sun is fully labelled G2V, a G2 dwarf on the main sequence. The red shoulder star of Orion, Betelgeuse, is a Class 1 red. Supergiant, Aldebaran, the orange eye of Taurus, is a Class 3 giant. In just 2 short symbols the system pins down both a star's temperature and its rank in size. The physical lever behind the luminosity class is surface gravity. A giant or supergiant has a radius tens or hundreds of times larger than a dwarf of the same mass, so its surface gravity and the pressure in its atmosphere are far lower, and pressure leaves a visible mark on the spectrum. In the dense, high-gravity atmosphere of a dwarf, atoms are constantly jostled by collisions that smear their energy levels and broaden the spectral lines. In the thin, low-gravity atmosphere of a supergiant, those same lines stay narrow and sharp. A trained eye, or today an automated pipeline, reads the width of the lines to assign the class. From one spectrum then come two coordinates, temperature and size, and with those two numbers in hand, a star can at last be placed on the single most important diagram in all of astrophysics. But first we need the relation that ties a star's size, temperature and power together, and it is one of the most useful equations in astronomy, the Stefan-Boltzmann law. A star's luminosity equals its surface area multiplied by the fourth power of its temperature, times a fundamental constant. That fourth power dependence is fierce. Double the temperature and you get 16 times the power out of every patch of surface. Written in solar units, the relation becomes wonderfully simple. A star's luminosity in suns is its radius squared times its temperature to the fourth, each measured relative to the sun. Give me any two of luminosity, radius and temperature, and this one equation immediately hands me the third. It is worth seeing this in action. Take Betelgeuse, with a cool surface of only about 3,600 degrees, but a luminosity of roughly 100,000 suns. Rearranging the Stefan-Boltzmann law to solve for its radius, the cool temperature and the vast luminosity together demand a radius of around 800 times the sun's. That is, a star so enormous that, set down where the sun sits, its surface would swallow the orbit of Mars. This is the defining trick of a supergiant, a relatively cool surface which radiates rather feebly per square meter, can still produce a staggering total output if only the radiating surface is large enough, and Betelgeuse's is almost unimaginably large. There is a catch running through all of this, and it is distance. What we actually measure at the telescope is not luminosity but apparent brightness, and the two are linked by the inverse square law. Brightness falls off as the square of the distance. To turn an apparent brightness into a true luminosity, you must know how far away the star is, and for most of astronomy's history that was the hardest thing of all to find out. The geometric gold standard is parallax. As the Earth swings around its orbit, a nearby star appears to shift its position slightly against the far more distant background, and the size of that tiny shift gives the distance directly. In the last decade, the European Gaia mission has measured such parallaxes for well over 1 billion stars, and in doing so has utterly transformed our ability to map the stellar sky. Brightness itself is recorded on a scale that is a genuine relic of antiquity, the magnitude scale, handed down from the ancient Greeks and both backwards and logarithmic. Brighter objects have smaller, even, negative magnitudes, and the scale is fixed, so that a difference of 5 magnitudes means a brightness ratio of exactly 100. The apparent magnitude, how bright a star merely looks from Earth, hopelessly blends together its true power and its distance. So astronomers define an absolute magnitude, the magnitude the star would have if it were placed at a standard distance of 10 parsecs, which strips the distance away and leaves a clean measure of intrinsic brightness. The gap between the two, called the distance modulus, is itself a direct measure of how far away the star lies. One last subtlety completes the brightness story. A magnitude measured through a single filter captures only the light in that one band, but a hot star pours out much of its energy in invisible ultraviolet and a cool one in the infrared. To track a star's true total output, you need the bolometric magnitude, which adds up the light across all wavelengths, reached by applying a bolometric correction to what you actually measured. In 2015, the IAU finally standardized the 0 point of this scale, tying a bolometric magnitude of 0 to an exact luminosity and fixing the sun's bolometric magnitude at 4.74. With that convention in place, measurements from wholly different instruments and surveys can be combined without contradiction. The unglamorous but essential bookkeeping that lets modern astronomy work at the scale of billions of stars. Now at last we can build the diagram. Plot a large population of stars with luminosity running up the vertical axis and temperature along the horizontal, with temperature, by a stubborn historical convention, increasing to the left, and something extraordinary appears. The Hertzsprung-Russell diagram, devised independently around 1910 by the Dane Ejnar Hertzsprung and the American Henry Norris Russell is the single most powerful organizing tool in stellar astrophysics. Stars do not scatter randomly across it, they fall into a few sharply defined regions, and each region turns out to correspond to a distinct physical state of stellar existence, so that the diagram is at once a census, a family portrait, and a map of stellar life and death. The dominant feature is the main sequence, a diagonal band sweeping from hot, luminous blue stars at the upper left down to cool, faint, red stars at the lower right. Around 90% of all stars lie along it, and crucially it is not a path that a single star travels, but a sequence ordered by mass. Every star on the main sequence is doing the very same thing, steadily fusing hydrogen into helium in its core, and where it sits along the band is set almost entirely by how much mass it was with. The massive stars burn hot and brilliant at the top, the feeble red dwarfs sit at the bottom, and our own sun sits, quite unremarkably, right in the middle at G2V. Away from the main sequence lie the other great populations. Up and to the right sprawl the giants and red giants, stars that are cool yet luminous, because although their surfaces are not especially hot, their radii have swollen to tens of times the sun's, giving them an enormous glowing area. These are stars that have exhausted the hydrogen in their cores and begun to die. Higher still are the supergiants, the most luminous stars in existence, up to 1,000,000 times the sun, ranging from red Betelgeuse to blue Rigel. And far below the main sequence lie the white dwarfs, the exposed, Earth-sized cinders left behind by ordinary stars, still hot enough to glow white, yet so tiny that they are almost invisibly faint. And because a star's luminosity is fixed by its radius and temperature together, lines of constant size run diagonally across the diagram, which is exactly why giants, dwarfs and white dwarfs of similar temperature end up in such wildly different places on it. The Hertzsprung-Russell diagram is therefore three things at once: a snapshot of a stellar population, an evolutionary map along which stars trace paths as they age, and a distance measuring tool, since matching a cluster's observed main sequence to a calibrated one yields the cluster's distance. Its modern triumph is the Gaia color magnitude diagram, built from precise distances and brightnesses for tens of millions of stars, which renders the main sequence, the giant branch, and the white dwarf trail in breathtaking, needle-sharp detail. Underlying everything on that diagram is one master variable: mass. A star's mass sets its central temperature and pressure, and therefore its fusion rate, its luminosity, its size, its lifespan, and its ultimate fate. Yet mass is the single hardest fundamental property to measure, because on its own it leaves no fingerprint in a star's spectrum. The one reliable way to weigh a star is to watch it dance with a companion. In a binary system, applying Newton's version of Kepler's third law to the orbit, relating the size and the period of the orbit to the total mass, yields the masses of the two stars directly. Eclipsing binaries whose spectra reveal both stars give the most precise stellar masses we possess, and it is these that quietly calibrate everything else. When luminosity is plotted against mass for main sequence stars, a steep and remarkably clean pattern emerges. Luminosity rises as roughly the 3.5 power of mass. Double a star's mass and you multiply its light output by more than tenfold. The exponent is not quite universal. It steepens for intermediate stars and flattens for the smallest red dwarfs, but the essence is simple, and it follows straight from the physics of stellar structure. A more massive star must run a hotter, denser core just to hold itself up, and, because the rate of nuclear fusion depends so violently on temperature, even a modest increase in mass sends the power output soaring. Mass is the throttle, and the engine responds ferociously. This single relation carries a profound consequence for how long stars live. A star's lifetime is roughly its fuel supply, which scales with its mass, divided by its burn rate, which scales with its luminosity, so lifetime falls as mass to the -2.5 power. Massive stars are spendthrifts. A 40 solar mass O star races through its core hydrogen in only a few million years, while the sun will last some 10 billion, and the smallest red dwarfs can smolder steadily for trillions of years, far longer than the present age of the universe. This is why brilliant blue stars are so rare and so fleeting, why the bright stars in a cluster die first and let the cluster serve as a clock, and why the humble red dwarfs will outlive every other kind of star from a mere handful of measured numbers. Temperature, luminosity, mass, the whole life story of a star unfolds, and the taxonomy the Harvard women began, spectrum by spectrum, stands today as one of the most secure and beautiful achievements in all of science.